This time I'm going to look at the specimen paper for A2 Chemistry Unit 1. You might know it as Unit 4. It's further physical and organic chemistry, and that's for the CCEA specification for A2. So starting straight in with the multiple choice. In the new exam papers, you don't have to join the dots in the answer sheet or anything like that. You just simply answer on the paper. So question 1. Propanone reacts with iodine in the presence of an acid according to the equation. We've got CH3COCH3, that's the propanone, and iodine, and that gives us the CH3COCH2I and HI. So the most appropriate method for investigating the rate of reaction is A. Titrating samples with an acid, B. Titrating samples with sodium thiosulfate, C. Using a graduated syringe, or D. Weighing the reaction vessel. Well, we know that the graduated syringe and the weighing the reaction vessel aren't going to work for this because we're making two solutions. Titrating the samples with an acid is not appropriate here. You can see because it is an iodine substance that it's going to be thiosulfate is the best way. And number 2, heat is produced when magnesium reacts with sulfuric acid. So we've got Mg, which is solid, H2SO4 solution, MgSO4 solution, and hydrogen also produced. So which of the following is true for the reaction? So we've got 4 statements. The first one, delta S is negative. Well, if we look here, the entropy change, we're going from 2 species on the left to 2 on the right. So there's no change there in entropy. It says delta H is positive. Well, the question tells us heat is produced when magnesium reacts with sulfuric acid, so that's exothermic, so it's negative. So that's incorrect as well. So the first one's wrong, the second one's wrong. Delta G is positive. Well, for the reaction to occur, and it does occur, it tells you it reacts with sulfuric acid, delta G has to be negative. So that's incorrect too, which leaves us with D, the reaction is feasible at any temperature. Number 3, 1 mole of propanoic acid, 1 mole of methanol, and 2 moles of water were mixed and allowed to reach equilibrium. At equilibrium, 0.5 moles of methyl propanoate was present. The value of Kc for this reaction is, well, I'm just going to write a little equation here and then put in the values from the question. So I'm not even bothering with the actual formula for anything. I'm just writing the acid and the alcohol gives you the ester and water. So initially, we're told there's 1 mole of propanoic acid, 1 mole of alcohol, and 2 moles of water. And then at equilibrium, 0.5 moles of the ester is present. So if 0.5 moles of the ester is present, that means that 0.5 moles of these have been used. So we have 0.5 of acid, 0.5 of alcohol, and we also then are making an extra half a mole of water, so 2.5 moles of water. We look at the expression for Kc, it's the concentration of the ester times the water divided by the acid times the alcohol. So it's products of reactants, and then we sub in the values there, 0.5 times 2.5 for the ester and the water, and 0.5 times 0.5 for the other two, and that gives us an answer of 5. And we look at the values here. A was 1, B was 1.25, C is 5, and D is 10. So your answer for 3 is C. Now, number 4, which one of the following graphs shows a reaction that is first order with respect to reactant Z? So I'm going to rule this one out straight away because you see we have time and the concentration of Z on the, that's not the way you would see a graph drawn, so we can ignore that one. And then we look at these 3, A, B and D. So A, you see, is a straight line going through the origin. B is just a flat straight line, and D then is this sort of more exponential shape of curve. So we know that first order, as you double the concentration, the rate doubles, so it is A. Just for completion there, B would be, that would be 0 order, and D is more like a second order reaction. So you should know those, you should just be able to look at that and recognise the shape of the curve, but be careful, see it can be tricksy, so check the axes are correct. Now, number 5, which one of the following represents the units for Kc for the equilibrium shown? So we have the Haber process here, we've got N2 and 3H2 gives us 2NH3 in a reversible reaction. So Kc is the concentration of the products so that's NH3 and it's squared because there's 2 moles of it, over the reactants. So N2 is just 1 mole and H2 is 3 moles. So I like to just write the square brackets. So for the units, so it's units squared over units to the power 4. So cancelling out the top two gives this total then of units to the power of minus 2, which is mole to the minus 2 dm cubed, and that in the answers here is B. Number 6, which one of the following is the systematic name for the carboxylic acid shown below? So if we look at this acid and look at what's going on here, you can see starting at the acid group, if we go 1, 2, 3, 4, 5, 6, there are 6 carbons in the chain, so that's going to be hex. And then we start naming at the acid group, so it's going to be hexanoic acid. We also have this methyl group here on the second carbon, so it's going to be 2-methyl hexanoic acid, which is in fact C there in the answers. So just be careful. I think this, they'd like to draw it sometimes so it looks like 2 methyl groups, but in that case it was just part of the chain. Number 7, which one of the following compounds reacts with both lithyl and your phosphorus pentachloride? So we're looking for an acid, which is D, and just for completion then A is an alcohol, B is an aldehyde, C is a ketone, and D then is the acid, so it's the correct answer. And 8, which one of the following statements about the formation of an ester from ethanoyl chloride and propan-1-ol is correct? So it's just a matter here of knowing your facts for it. So conch sulfuric acid is not required, heat isn't required, the ester is not ethyl propanoate. If we look at this, it's ethanoyl chloride and propan-1-ol, so it's going to be an ethanoate from the ethanoyl chloride, so it has to be D. The reaction goes to completion. Number 9, butan-1-ol was reacted with an excess of propanoic acid in the presence of a small amount of concentrated sulfuric acid. 6 grams of the alcohol produced 7.4 grams of the ester. So 6 grams of alcohol give you 7 grams of the ester. Which one of the following is the percentage yield of the ester? So quite a bit of working out here to do for just the 1 mark. The first thing is to work out the formula mass of your butan-1-ol, which is C4H9OH. So the formula mass is 74. So the number of moles then of the butan-1-ol, so we've got 6 grams of that, so the number of moles is the mass divided by the formula mass, 6 over 74, so that's 0.081 moles. Just have to wait there for the iPad to save it. So then we know there's the same number of moles of the ester, also 0.081, and the formula mass of the ester, I've drawn it out here, so we have C2H5C double bond O and then O C4H9. The formula mass there is 180, sorry, not 180, 130. So 0.081 times 130 gives us 10.3 grams for the theoretical yield of the ester. And then when we look at the question, it says you actually got 7.4 grams. So the percentage yield is the actual yield divided by the theoretical yield. So 7.4 divided by 10.53 times 100 gives us 70%. And the final multiple choice question here, which one of the following salts will dissolve the solution with a solution with the highest pH? So in other words, the most acidic. So we're looking for something which is a strong base and a weak acid. So looking down the list, it has to start with sodium, and the only one then from a weak acid is the ethanoates. The answer here is D, sodium ethanoate. Now, number 11, we've got data for the reduction of iron 3 oxide by carbon, which are shown in the table below. We've got an equation for it. So 2Fe2O3 gives you, or plus 3 carbon gives 4 iron and 3 CO2. So we've got the table here with the substances, we've got the enthalpy of formation, and we have the entropy. So calculate values of delta H, delta S, and delta G for the reaction at 298 Kelvin. So delta H, you're looking at the sum of the enthalpy formation of the products, take away the sum of the enthalpy formation of the reactants. So when we look at this, it's 3 lots of the 3 lots of the carbon dioxide here. So it's minus 393.5 times 3. And then the reactants is the iron oxide. So 2 lots of that. 2 times minus 824.2. So it's products take away reactants. So overall that gives 467.9 kilojoules per mole. And of course, carbon and the iron are elements in their standard states. So their enthalpy of formation is 0, so they don't feature in that. Now, the entropy, the total entropy of the products, take away the total entropy of the reactants. And in this case, we have to use all those values. So putting in the products, so iron is 4 times the minus 27.3. I've got minus in there. It's 4 times 27.3. Then we've got 3 times the 213.6 for the carbon dioxide, so 3 moles of carbon dioxide. Take away, then we have 87.4 for the iron oxide, and you see there are 2 moles of it, and then 3 times 5.7 for 3 moles of carbon. Adding those all together, we get 558.1 joules per Kelvin per mole. And then delta G is delta H minus T delta S, so 467.9, and take away the T is 298, we saw that in the question earlier. And then the only place you can go wrong here really with these questions is if you don't convert from the entropy, which is in joules, into kilojoules. Okay, so that's why it's 0.5581. And overall then that is 301.6 kilojoules per mole. So 2 marks for the enthalpy, 2 marks for the entropy, and just 1 mark for Gibbs free energy. So using your results from part 1, explain why this reaction is not feasible at 298 Kelvin. Well, it's because delta G is positive, and if delta G is positive, the reaction is unable to happen. It must be negative for the reaction to happen. And calculate the temperature above which the reaction is feasible. So we're just setting here T to delta H divided by delta S. So we got 467.9 for the enthalpy change, entropy change 0.5581, so we get 838 Kelvin for that. Okay, next question is about lattice enthalpy. So the strength of the ionic bonding in compounds such as magnesium fluoride and magnesium chloride is related to the lattice enthalpy of the compound. Define the term lattice enthalpy. So 2 marks for this. It's the energy required to convert 1 mole of an ionic solid into gaseous ions. 1 mark for each of those. And the Born-Haber cycle for magnesium fluoride is shown, but there are bits missing. So we'll come back to that in a second. So using the data given below, calculate the lattice enthalpy for magnesium fluoride. So the first thing was to complete it. Sorry, missed that. So at the bottom then, it's for magnesium fluoride. So we're going to just write in MgF2 as a solid, and then we're going to plug in everything else around it. So you see here, we've already got the magnesium as a gas and the fluorine as a gas. So what has to happen then is in this one here, we need to have the magnesium solid and the fluorine as a gas. So they're in their standard states. So if we go up this way first, so we've got the magnesium solid and the fluorine gas. And then the next space is this one. So we're going from magnesium, which has been atomized here, so that's the enthalpy of atomization in this one, to the magnesium ion, so that's the first ionization energy of magnesium, so Mg plus as a gas, plus an electron, and the fluorine is still as a gas. So going up a step then to the next one, this is the second ionization energy of magnesium, so Mg2 plus, with 2 electrons now, and the fluorine is still F2 as a gas. And then at the top here, that would be in this last bit, we've got the atomization of the fluorine, so going from F2 to 2F atoms. So we've got the Mg2 plus as a gas and the 2 electrons, plus then the 2 fluorine atoms. And then following this arrow down the way, we keep the Mg2 plus, and we have then 2 fluoride ions. So that is the electron affinity of the fluorine. And then this one here is the one that we want to find out. So then, using the data below, calculate the lattice enthalpy for the magnesium fluoride. So I'm just going to try and keep these both there at the minute so that you can see what I'm doing. So the magnesium fluoride here, minus 1123, that corresponds to this value. I'm just going to highlight these in a different colour actually. We'll go for pink. So that's the value there, the minus 1123. Then just plugging in the other ones in the order they're in the table. The first electron affinity for fluorine is here, and because there's 2 moles of fluorine ions being produced, it's 2 times minus 348. Atomization enthalpy for fluorine is here. Again, there's 2 moles of the atoms being produced, so it's 2 times 79. Then the ionization enthalpy of magnesium, the first ionization enthalpy is this one, 736. Second ionization enthalpy is this one, is plus 1450. And then the atomization enthalpy of magnesium is 150. Now, if you've seen my videos before, you know the way I like to work these out is just I draw big arrows on, showing the direction on both sides. Of course, this is what we want to find. So everything on this arrow is going to be positive and everything in this arrow is going to be negative. So, for example, this one here, the 1123, I'm just going to have to change the sign of it. So when I plug these values in, that becomes the lattice enthalpy is the sum of all of these going up on the left, take away the ones going down on the right. So these are all positive and these are all negative. Okay, so we've got plus 1123 plus 150 plus 736 plus 1450 plus then the 2 times 79 for the atomization of fluorine, and then minus 2 times 348. And adding all of those together, it gives the answer as 2921 kilojoules per mole. So part C, magnesium fluoride and magnesium chloride are both soluble in water. Magnesium chloride has an enthalpy of solution of minus 155 kilojoules per mole. Using diagrams, show how magnesium and fluoride ions interact with water molecules in an aqueous solution of magnesium fluoride. So magnesium fluoride, you're going to have the Mg2 plus and the fluoride ions, and the magnesium is going to be attracted obviously to the lone pair on the oxygens, and the fluoride ion will be attracted to the slightly positive hydrogens in water. And you can see I've just drawn those as little dashed lines, so 1 mark for showing how each bit the magnesium and the fluoride ions interact. So given that the enthalpies of hydration of magnesium ions and chloride ions then are minus 1920 and minus 364 kilojoules per mole respectively, calculate the lattice enthalpy of magnesium chloride. So at the top here, part C, it gives you the value of minus 155 for the enthalpy of solution. So then we're just taking away those other values. So minus 1920 for the chloride ions, for the magnesium ions, and then 2 lots of the chloride ones, 2 times minus 364, and punching that into the calculator, you get minus 2493 kilojoules per mole. 13. Butanone reacts with hydrogen cyanide to form a product that contains an isometric centre, and here it is. So we've got 1, 2, 3, 4 groups around this chiral carbon in the centre. So the reaction mechanism is similar to that for the reaction between hydrogen cyanide and propanone. Give the systematic name of the product. So we're looking here for the longest chain. So 1, 2, 3, 4 along here. That is a 4-carbon chain with a nitrile group on it. So that's going to be a butane nitrile. And then this hydroxy group and the methyl group are on the same carbon, which is the second one. And they go in alphabetical order. So 2-hydroxy, 2-methyl, butane nitrile. What type of stereoisomerism is shown by the product? Well, optical isomers. You've got your chiral carbon center, so that has to be the answer. And then it's just a matter of drawing the 3D representations of the stereoisomers. So we have the carbon in the middle with the methyl group, the hydroxyl group, the nitrile group, and then the ethyl chain. And here, just the same thing with the mirror image. And remember to draw your little mirror as the dotted line down the middle. The name for the mechanism then is nucleophilic addition. And then drawing the mechanism for the reaction. So we've got the aldehyde here with the CN minus the nitrile attacking, and you can see I've drawn in that the electrons from the double bond are moving to the carbon, and the electrons from the lone pair here are moving to the carbon, and then from this double bond, one of them is moving to the oxygen, and that leaves us with this species here with an O with a lone pair of electrons and a negative charge, and then the nitrile group attached. And then what happens is the lone pair on this negatively charged oxygen moves to the hydrogen, so we end up with an OH group here as well as the nitrile group then. Part 6, explain in terms of the mechanism why a racemic mixture is produced in this reaction. Well, the key here is that the carbonyl group is planar, so the nucleophile doesn't have any advantage from either side, so it attacks equally from both sides, so you get equal amounts of each optical isomer. And of course, equal amounts means a racemic mixture. Now, butanal is a structural isomer of butanone. Describe, giving practical details, how you would carry out a chemical test to distinguish between samples of butanal and butanone. So we're looking for something that tells us whether it is an aldehyde or ketone, so you have a choice of 3. The first mark here was for saying you'd heat it with, and then you could either say Tollens reagent, failing solution, or acidified potassium dichromate. And then you needed to say that there was a positive result with butanal and no change with butanone. Obviously you need to quantify that as to what the positive result is. So with Tollens, it's the silver mirror. It's taken so long to save the image today, it's killing me. So the failings then is blue solution gives you a dark red precipitate if it's positive, and the potassium dichromate gives you a colour change from orange to green. Now, next bit, 2,4-dinitrophenyl reacts with both butanone and butanal to form 2,4-dinitrophenyl hydrazones. So write the equation for the reaction of butanone with 2,4-DNPH. So this is our butanone. We've got the CH3C double bond O, and then CH3CH2 on the other end. And then this is our DNPH. So we have the benzene ring with 2 nitrate groups, and then we have this NH2NH group attached. So this joins, of course, here, and so we get the double bond between the carbon and the nitrogen there, and also water being produced. The hydrogen is being lost from here, and the oxygen from here. Number 14, acid dissociation constant Ka for propanoic acid is 1.35 by 10 to the minus 5 moles per dm cubed. A buffer solution can be prepared by mixing a solution of propanoic acid with a solution of sodium propanoate. Write the expression for the acid dissociation constant of propanoic acid. So Ka is going to be the concentration of the anion times the hydrogen ion concentration divided by the concentration of the acid. Then calculate the pH of a 0.25 molar solution of propanoic acid. So from this equation, we're just going to take it then that the top two terms here are the same. So I'm just writing Ka is concentration of hydrogen ions squared divided by the concentration of the acid. So when I rearrange that, then I'm getting that the hydrogen ion concentration is 0.00184 mole per dm cubed. pH is the negative log of the hydrogen ion concentration, so negative log of 0.00184 gives us 2.74. So what is meant by the term buffer solution? So it's a solution which minimises changes in pH on addition of small amounts of acid or alkali. So 1 mark for the top bit, 1 mark for the second bit there. Then you have to calculate the pH of the buffer formed when 300 cubic centimetres of 0.25 molar solution of propanoic acid is mixed with 200 cubic centimetres of 0.15 molar solution of sodium propanoate. So, working out the moles of acid, 0.25 times 0.3, so 300 cubic centimetres is 0.3 of dm cubed, so 0.075 of it. And then the moles of the salt, 0.15 from here times 0.2, because it's in 200, gives us 0.03. So the total volume of the whole thing is 500 cubic centimetres. And I've just written here the concentration of the acid is 0.15, the concentration of salt is 0.06. So the hydrogen ion concentration then is Ka times the concentration of the acid divided by the concentration of the salt. And that means we have 3.38 by 10 to the minus 5 as the hydrogen ion concentration. Then putting that into your calculator, the negative log 10 of that number, 3.38 by 10 to the minus 5, we get 4.47. Next, a titration curve shows the change in pH when a 0.2 molar solution of sodium hydroxide is added from a burette to 25 cubic centimetres of propanoic acid of unknown concentration. Write the equation for the neutralisation reaction which occurs. So we've got our propanoic acid here and NaOH, so CH3, CH2, COOH plus NaOH gives CH3, CH2, COO, Na and H2O. So really it's this part that they're looking for to be correct. Then suggest a suitable indicator for this titration, give the colour change and explain why the indicator is suitable. So looking at this, we see a very straight section here. In the pH, we know that we have sodium hydroxide, so a strong alkali, and we have propanoic acid, which is a weak acid. So the best indicator choice here is going to be phenolphthalein. And of course the colour change would be from colourless to pink. And the reason you're going to give is because it's in a range that matches the vertical section of the titration curve. Then calculate the concentration of the propanoic acid, taking the values from the question at the top of the page. Number of moles of sodium hydroxide is 0.2 times 18.5, that's from the graph here. Divide by 1,000, so 0.0037 moles of sodium hydroxide. It's going to be a 1-to-1 ratio, so we're going to have 0.0037 moles of the propanoic acid in 25 cubic centimetres. So overall then the concentration is 0.148 moles per dm cubed. So you're just multiplying that by 40 to get it up to the moles in a litre. Part 4, 25 degrees, Kw has the value 1 by 10 to the minus 14 mole squared dm to the minus 6. Calculate the pH of a 0.2 molar solution of sodium hydroxide. So Kw is the concentration of the hydrogen ion times the concentration of the hydroxide ion. So rearranging that, so we've got the hydrogen ion on the left, we've got Kw with OH minus concentration. Work that out, it gives you 5 by 10 to the minus 14 moles per dm cubed. And then the pH from that negative log, the hydrogen ion concentration, so it's 13.3. Number 15, benzene is toxic and carcinogenic. However, the reactions of aromatic compounds can be studied in the laboratory using other substances such as methyl benzoate. So the electrons in the pi bonds in benzene are delocalized, Draw two structures for benzene to show the p orbitals before and after delocalization. So before, you see I've got the little benzene ring here, and we've got the little sort of figure of eight shaped orbitals going on there. And then afterwards you can just about make out the little ring in the middle, and then we've got these two areas above and below the ring of delocalized electrons. Nitration of methyl benzoate can be achieved using a nitrating mixture of concentrated nitric and sulfuric acids. Write an equation to show how these two acids react when mixed. So we've got HNO3 and 2H2SO4, and that's going to give us this NO2 plus and H3O plus and 2HSO4 minus ions. Then the name of the ion produced in this reaction, which attacks the methyl benzoate molecule, is of course the nitronium ion. And draw the mechanism of the mononitration of methyl benzoate and name the mechanism. So the mechanism is electrophilic substitution. And looking at it more closely here, this is our benzene derivative. You see the electrons moving from that delocalized ring in the middle. We've got the NO2 plus here, the electrons are moving towards it. And then in this part you see we have this partial ring with positive charge, and we have here the NO2 and the hydrogen both attached. And then what happens is the bonds in that, the electrons in that bond move towards the middle, and we're left then just with the NO2 group, and the hydrogen ion then is liberated. Name the organic product of this reaction. Well, it is methyl 3 nitrobenzoate. And the appearance of this is a cream solid. Now, this is a longer question, a 6-marker. So the way it was marked, to get 6 marks, you had to get 7 indicative points. 4 marks was for 4, and 2 marks for 2 points. So describe how you purify the product obtained and confirm its identity. So you would first of all have to recrystallize, then filter off the crystals using vacuum filtration, dry the crystals, place some solid in a melting point tube, heat it slowly using the melting point apparatus, record the temperature the solid starts and ends melting at, then repeat and average the temperatures, and then compare with known values in data tables or a data book. Number 16, the ionic equation for the alkaline hydrolysis of C4H9Br is shown below. So this is the equation here. We've got that plus the OH minus gives us C4H9OH, which is butanol, and then the bromide ion. So data for the reaction is given in the table. So we've got the initial concentration of the bromobutane, the hydroxide ion, and then the initial rate for each. So first of all, what's the order of the reaction with respect to the bromobutane? So you see here, if we go from number 2 to number 1, the concentration's doubling, and we're going from 20 to 40, so that's doubling as well. So using that one, it's first order, and I've just said comparing experiment 2 to experiment 1, the concentration doubles from 2 to 1, and the rate also doubles. Then what's the order with respect to the OH minus? So if we look at 1 and 2, they're both the same, 0.02, and going to 3, then it's doubled to 0.04. Now, when you look at 2 and 3, you might think, oh yeah, well, that has had an effect, it's tripled it. But actually, looking here, it's the effect of the tripling of the concentration of bromobutane that has done that. So if we go from 0.2 to 0.2 and 1 and 2, the concentration of that hasn't changed, but the concentration of the bromobutane is halved, and that's what's caused the effect. So basically I'm saying there's no effect on the rate, so it's 0 order. Right, the rate equation for the reaction, so because the hydroxide ion isn't involved, rate is K, and then C4H9Br in the square brackets. Calculate the value for the rate constant and give its units. You're just picking one from the table. So K is the rate divided by C4H9Br concentration. So I've taken 40 as the rate and 0.02 as the concentration, which gives 2000. And the units then, we have rate divided by concentration. So mole dm seconds to the -1 over mole dm, mole dm to the -3 seconds to the -1, divide by whole dm to the minus 3, which gives us seconds to the minus 1. 1 mark for the number, 1 mark for the units. Draw the reaction mechanism for the hydrolysis of the bromobutane, which is consistent with your rate equation. Show the structure of the bromobutane clearly in your mechanism and identify the rate determining step. So here I've drawn my bromobutane, 1, 2, 3, 4 carbons and the bromine here, and you can see I'm showing the movement of electrons from that bond to the bromine, and that is the rate determining step, and it produces this carbocation and the bromide ion. And then the hydroxide ion attacks here the electrons from the lone pair going to the carbocation, and we end up then with the alcohol, where the OH has been substituted for that bromine. And there's 1 mark for each error made there in the mechanism. Finally, number 17, fats and vegetable oils are triesters of long-chain carboxylic acids. Base catalyzed hydrolysis of an oil produces glycerol and the sodium salt of an octadeca 9,12-dianoic acid as the only product. So this is the octadeca 9,12-dianoic acid. So we'll come back to that. Draw the structure for glycerol. You should know that straight away. I always draw it going down the way. So CCC, 3 carbons in a row. Each of those then, you're putting the hydrogens on them, and then on the right hand side there's no H group on each. Then the systematic name for glycerol is propane 1,2,3-triol. And then the structure of the oil, so that's where we need this octa-9,12-dianoic acid, and it's just a matter of, this is the stem here from the glycerol, and then we're putting in that big long chain to the right each time. So you see here each of those is carbon with a double bond to the oxygen, CH2 7 times, CH, and then double bond CH, CH2, CH, another double bond CH, CH2 4 times, CH3. Let's just copying it carefully across, folks. And simple monoesters, such as the one shown below, can be prepared by reacting carboxylic acids with alcohols. And here is our little monoester. So give the systematic names of the carboxylic acid and the alcohol required to prepare this ester. So you see we've got this bit and this bit. So go for the easy bit first. So the alcohol would have been methanol, just you got this methyl group here. So it's methanol, and then the acid, so this would have been the acid group, and then there's 4 carbons in the longest chain. Can you see that? 1, 2, 3, 4. So it's a butanoic acid, and we have this methyl group attached to the 3rd carbon. So it's 3-methyl butanoic acid. Then write the equation for the formation of the ester. So we've got the acid here and the methanol, so that's the 3-methyl butanoic acid. And then it's giving us the ester, where I've just substituted in for this hydrogen. We've got the OCH3 and water. And then finally describe, giving experimental details, the preparation of a pure dry sample of the ester. So again, if you got 6 indicative points here, you got 6 marks, 5 was for 4 marks, and 4 points was for 2 marks. So quite a lot of detail needed for this longer question. So first point, put the acid and the alcohol into a round bottom flask and add conc H2SO4 slowly. Then add anti-bumping granules, then heat under reflux, distill and collect at the boiling point of the ester, then shake with aqueous sodium carbonate and release the pressure. Separate the ester layer using a separating funnel, then add a drying agent, you'd have to name that, so whatever you've used which is appropriate, and then decant or filter it.